has a grain fineness number of around 90 to 140 grain fineness number. And another important aspect of this sand is the clay content should be 0. Ideally it should be 0, but anything less than 1% is acceptable over here. The grain fineness number and the grain size are chosen so as to minimize the surface roughness developed in the casting. That is a very important characteristic over here, that the surface roughness is desired to be at the minimum over here. Now synthetic resins are generally used. The synthetic resins are generally used over here with respect to thermosetting resins, which get hardened as heat is transported into them. The resin that is most widely used is phenol formaldehyde, because it provides very high strength and is resistant to heat. It reacts at a very high temperature, so it is resistant to heat. Additives are also added over here, and the additive is added with respect so as to improve the surface finish and avoid any thermal cracking which might develop into the system during the pouring of the sand. Additives that are commonly used are coal dust and calcium carbonate, but depending upon the type of casting you are doing, you have ammonium borofluoride and magnesium silicofluoride also. Manganese dioxide is only used when you know that a lot of reactive gases are going to be developed. Only then we use manganese dioxide. Otherwise we use coal dust, pulverized slag or calcium carbonate. Lubrication is required so as to ensure that the sand particles flow very easily and comfortably across the mold, inside the mold box. That is very important aspect over here. So what we do over here is that we use calcium stearate and zinc stearate as a lubricant depending upon the type of metal that we are casting. So in this table, what I am trying to show to you is that with respect to different casting metals, the composition of this sand for shell molding is different. Like for carbon and alloy steels, silica and zircon sand is added together, followed by resin and additives. Whereas if you are using medium or high carbon steel, then silica sand is not used. We use zircon sand, and zircon sand is an artificial sand, to be precise. It contains lot of properties which are man-made and different from sand particle, from silica sand. Similarly, what you observe over here is that when you are using basically the gray cast iron, in that case what you are having is silica as well as zircon together, but additives are not mixed in a higher proportion. Additives are very slow. So different materials will have different composition of sands that can be utilized. Now, how is shell molding done? I'll give you a brief idea how this process actually takes place. Now, what you see over here is the first thing that you need to prepare is the sand for the shell molding. So what we do is, first of all, we take the sand, the additives, they are first of all completely dried, and then they are put in a muller, sand muller, for a period of 1 minute so as to achieve homogeneous mixing. Once the 1 minute period has passed on, then the liquid resin is added and mixing is continued for another 3 to 5 minutes. As the mixing is taking place, what we also ensure is through an air dryer, we pass hot and warm air into the muller while the mixing process is going on, so that any moisture or any liquid that is present in the mixture is completely drained out, and the coating of the phenol formaldehyde and additives on the sand particles becomes to the desired property. So once that has been done, then generally what we do is that once we have taken a metal for preparing patterns, because gray cast iron is generally taken over here because of easy availability and excellent stability of temperatures. Now what we do is we prepare a match plate or a cope or a drag metal pattern. We use a metal pattern over here. We develop that metal pattern, and on top of this molding box, this metal pattern is placed and clamped together. So what you see is the dump box, and inside the dump box you will have the sand that you have prepared in step number 1, and the pattern which is placed upside down, inverted pattern is placed over here. Now what you do is you basically heat the pattern so as to take it to a higher temperature, because the sand contains thermosetting resins, and when the thermosetting resin comes in contact with a metal at an elevated temperature, it starts to react and forms the bonds. So that is the reason why this pattern is going to be heated over here. Now once the heated pattern is there and the box and the sand is there, the dump box is completely inverted. The dump box is inverted by 180 degrees. And once it is inverted, what happens is the sand particles fall on the pattern. And the pattern is in a heated state. So the sand particles comes and reacts with the heated metal plate, thereby causing the hardening of the grains. The phenol formaldehyde, the resin and the other parts, they start to harden. And as they harden, what happens is they also entrap the sand particles with them. So after keeping it for around 5 to 10 minutes in this position, the box is again inverted back to the original position. And now what you see over here, that a shell has developed across the pattern. A shell has developed across the pattern. Now what we do is we remove these two clamps and take this pattern out along with this shell. And this is taken to an oven for curing process, and it is kept there for the period of around 10 to 15 minutes so that the curing process actually takes place. So once the curing process has taken place, then using a small chisel hammer and minimum contact, this shell is removed from the pattern. Now this pattern is taken out and the shell becomes the replica of the casting that you desire to make. So the different halves of the part that is required to be made are prepared in this way, and they are assembled inside a flask and clamped together such that this becomes the pouring gate, and the metal goes directly inside, and the molten metal is poured inside, and after solidification has taken place, the finished casting with a sprue is removed from the box or the flask. So this is the process of shell molding, and it's a simple process. But the knowledge of preparing the shell is something which is very important for the operator to understand. The basic advantages of shell molding are that the surface roughness that you obtain in shell molding is far lesser than the surface roughness that you obtain through sand casting. The finishes on the range of around 2.5 microns or less than 2.5 microns can also be achieved. Another very important aspect is the dimensional accuracy. Now, if dimensional accuracy of 0.25 mm is possible, especially in a small part, on a big part this ranges from 0.5 to 1 millimeter. The surface finish and accuracy basically eliminates any requirement for further machining, and the collapsibility of the mold is sufficient to avoid any tearing or cracking during the casting process. So surface defects as well as surface finish, surface roughness is actually eliminated in this process. But the problem is this process is more expensive because it requires a metallic pattern first of all, and secondly the process is done in a far more number of steps and requires a mold metallic pattern as well as a molding box which has to be metallic in nature. So if you are making a casting in small quantities, then it is very difficult to justify that. The other disadvantage of shell molding is that if you are having a big casting to be made, then it is very difficult to prepare a large size casting out of this process. Generally, steel castings are generally made of less than 10 kgs over here. Another disadvantage of shell molding is that if the phenol formaldehyde and the additives are not mixed properly, and if there is no smooth flow of the sand during the inversion and back inversion process, then you might not get a homogeneous sand mold, and that might create a lot of defects in casting. So having a very good understanding of sand and chemical particles is very important over here. So experience matters in shell molding a lot. So next, what I want to discuss is the process of centrifugal casting. Now, what is centrifugal casting? Centrifugal casting is basically a combination of different methods of casting, which uses centrifugal force to distribute the molten metal to the outer regions of die cavity. Now, if you are trying to make something of a hollow nature, like a hollow pipe or hollow small parts like this hollow washer, then you can utilize this centrifugal casting to create the casting. A very important aspect and a very important advantage of centrifugal casting is the segregation of the slags and oxides. Because slags and oxides are lighter in density, so they get separated and get segregated towards the center, whereas the pure metal is denser and it goes on the outside. So using the centrifugal force basically creates a very good segregation of pure metal and impurity can be removed by post-processing process later on. So there are three types of centrifugal casting processes. There is a true centrifugal casting, there is a semi-centrifugal casting, and there is centrifuging. These three processes are actually named on the basis of the size of the casting that you are trying to create. True centrifugal casting creates bigger dimension castings, bigger products. Semi-centrifugal casting creates a product which is medium or small in size, whereas centrifuging basically creates a product which is very small in size. So these three names are basically given because of their basic concept is same, that is centrifugal force is going to act, but the size of the casting that is being generated defines according to these three names. So let us go to the true centrifugal casting first. Now in true centrifugal casting, you have got a mold, and that mold is not a small mold, it's a big mold ranging from 0.5 meters to more than 5 or 10 meters also. So you can have a big mold over here. And now suppose you want to make a hollow pipe over here. So true centrifugal casting is one of the best processes to create a hollow molding. Now this process is actually in two types, horizontal as well as vertical process, that both I'll explain to you. So the main parts that are made through this process are basically tubes, pipes, bushings and rings. And how does this system work? So if you can see, there are two rollers. There is a free roller and there is a drive roller. So what we do is we attach a motor onto the drive roller, and these two rollers are attached to the mold by contact. So when this drive roller moves and the free roller also moves in the same direction, this mold will move in the opposite direction. Okay? And when the drive motor speed is increased, the mold will also rotate at a higher speed. As a result, it will generate the centrifugal force and the segregation of the molten metal takes place. Now, what happens is, in centrifugal casting, you don't simply put the metal and then start rotating. In large castings, basically what you require to do, or what is desired to do, is continuous pouring of the molten metal into the mold has to take place so as to maintain homogeneity during the molding process. So what happens is, now when this starts to rotate and molten metal is poured inside over here, so this mold also starts to rotate, and molten metal starts to stick to the inner diameter of the mold. It starts to stick to the inner diameter of the mold, thereby creating a very good segregation and a hollow cavity. Now, as I said, the centrifugal casting is defined in two different forms. One is horizontal form and other one is vertical form. In horizontal form, basically a centrifugal force is basically defined by F is equal to mv square by r, where F is the centrifugal force, m is the mass, v is the velocity of rotation, and r is the inside radius of the mold. So now if I go back, this is the inside radius of the mold. So this is the inside radius of the mold that you have got. So now a very important factor is called G factor, which is the ratio of centrifugal force divided by weight. Now this G factor actually defines which type of a centrifugal casting process should be utilized for which type of a product. Now if you have got a L by D ratio of very small L by D ratio, then it is better to have horizontal system. But if you have an L by D ratio very long, it is recommended that you use either horizontal or vertical also can be used. So G by F is given as F by weight of the weight of the casting. So F is equal to mv square by r and W is equal to mg. So GF is equivalent to V square by rg. Now what is velocity over here? Velocity is 2 pi rn by 60. So velocity is 2 pi rn by 60. So divide 2 by 60, we have pi rn by 30, where this 60 basically converts the speed from seconds to minutes. So now we know what will be the value of n over here. So once I know what n is rotational speed, so substituting this expression over here, the velocity of v becomes pi rn by 30 whole square divided by rg. So this becomes r into pi n by 30 whole square divided by g. So by rearranging this equation, basically I can find out what will be the rotational speed in order to generate a sufficient G factor, which will help in creating a good centrifugal casting. So n is given as 30 upon pi 2g capital G into F, where small d is the inside diameter of the mold and outer diameter of the casting. I want to explain that again. Now this lining, the second lining that you see, that is the inside diameter of the mold and outer diameter of the casting. So this is the lining that we are talking about. So if G factor is too low, then the liquid metal will remain forced against the mold wall. Whereas if it is too high, it will be concentrated towards the center. So it has been found by research by various researchers that the GE force of around 60 to 80 is appropriate for horizontal centrifugal casting. Now in case of vertical centrifugal casting, basically what happens is the lower section is thicker and the upper section is thinner. That is what you observe over here, that the lower section or the section near the base of where the casting process is taking place, that will be thicker and that top section will be thinner. So in order to obtain the speed of rotation, the formulation actually is devised as 30 upon pi under root 2 GL upon RT minus RB, where RT is the inside radius at top of casting and RB is inside radius at the bottom of the casting. And this equation is basically very dependent on you should know what is going to be the casting diameter at top and bottom. So solidification shrinkage at the exterior of the cast tube over here is not a factor, but centrifugal force continuously relocates the molten metal towards the mold wall during the freezing process, because metal is being continuously poured into the system and it is being rotated at a very high speed. So what happens is whatever shrinkage is taking place, it is being compensated by the new metal which is coming into the system. As a result, solidification shrinkage at the exterior is always taken care of. What you find over here is any impurities, if any present, that will be either slag or it will be the particles which are not melted, they will come toward the inner wall and they can be removed after machining, but if it is required at all. Now, what is semi-centrifugal casting? Now, in semi-centrifugal casting, what you are basically trying to do is you are using a small product like a hollow plate. If you use a hollow plate, that can be developed through centrifugal casting. So let us assume that we are making a hollow plate with a thickness of say around 5 mm and a diameter of around say 50 mm with an inside hollow diameter of 5 mm. So we are going to create a hollow plate like that. So what happens is we use a small molding box or a flask which is filled by sand, basically, which is filled by sand, and what happens is it is fixed onto a platform which is basically attached to a motor. So this platform that you see over here, this platform can rotate. So this platform can rotate. So what happens is, once you have prepared this mold, now this mold can be a sand mold or it can be a metallic mold, whatever you want, but generally it is a sand mold. Metallic mold is not preferred over here. And you have got a basically feeding system available over here through which molten metal is going to be poured into the system, and molten metal goes and settles just like that. It settles just like that. And after that, what happens is this whole table is going to be rotated at a very high speed, at a very high speed. The speed ranges from 30 revolutions to 50 revolutions per second, or per around 300 revolutions per minute. So it rotates at a very high speed. So when it rotates, what happens is the molten metal actually segregates towards the outer side, and the center side becomes almost either metalless or devoid of any significant amount of material. It will be having a small metal. So what happens is you have a pouring basin. So as it is rotating, you can keep pouring in the molten metal, and the metal starts to solidify at the extreme ends of the casting. And then it is allowed to solidify. It is allowed to solidify. So while solidifying, what happens is you prepare a typical casting of this dimension. Okay. Typical casting of this dimension, which is given by brownish color. So what you do is you remove the mold box, you take out this complete casting, and then what you can do is you can simply eliminate the portion of the casting where the quality is at the poorer or the quality is lowest. So what you can generate is a hollow section at the center and a significantly strengthened and reinforced system at the periphery. So you get better strength over there on the periphery as you desire. So wheels and pulleys are a classic example that are made by this process. Now let us come to the third part. The third part is basically centrifuge casting. Now centrifuge casting is something which is similar to semi-centrifugal, but the only difference over here is the part is even smaller than that. It's a very small part of say 1 mm, 2 mm, and you can make multiple parts over here. So since the part size is very small and the mold box is bigger, so you can make 5, 10, 15 parts in one go over here. The only thing that you need to provide is the runner system and the pouring basin to those components. Other than that, the whole process remains the same, that there is a platform which can be rotated, and on top of that platform you have a flask which is filled by sand, and you create a riser and a runner system for that. And then you start to pour metal and start to rotate this table at a very high speed. And the same process of centrifugal action takes place where the metal is transferred towards the periphery of the runner system and it gets connected into the cavity that is formed, mold cavity, and parts are going to be generated. The only difference in centrifuge casting is the part size is very small, and it can have radial symmetry, and smaller parts can be fabricated out of this system. So this is all about the two casting processes that we learned today. Thank you. So if you have any questions, please unmute yourself and ask.